Thank you very much, Aaron. So we'll take some time for a few questions here. Yeah.
You know, you mentioned that the mass of the black hole is about 0.1% of the mass of the bulge of the galaxy.
Yeah.
First of all, how do they measure the mass of the bulge of the galaxies? And does that imply the Milky Way bulge is only 4 billion solar masses?
Yes, so I'll answer the second question first. The Milky Way has a relatively small bulge component. It's most of the mass of stars in the Milky Way is in the spiral disk and not so much in the bulge. The way you measure the mass of the bulge, well, there are two possible ways. One is by adding up all the starlight that you see. You can directly observe the starlight. We know what kinds of stars are contributing to that, and we know the masses of different kinds of stars. So we can add up essentially the contributions of the masses of all those stars just from the light that we see and estimate the amount of mass in the stars in the bulge. Another way to do it is by using similar techniques, using orbital motions in the bulge of the galaxy, because the bulge is orbiting, stars are moving around in it, and if we can measure the dynamical properties of the bulge, we can essentially use the orbits of stars as a dynamical probe of the mass as well. So there are a few different methods that we can use.
So there's a really important question right over here at the edge. Yeah.
Okay, the question was, would astronauts ever drop space probes in a black hole? And I think probably the answer is we would if we could, but we can't. Because black holes are so far away that we can never really get close to them. The farthest away that any astronaut has ever been away from the Earth is the moon. And that's pretty close in terms of these giant cosmic distances. So all of these black holes that I'm talking about are enormously far away compared to the distances that astronauts can travel, or even the distances that we can send robotic space probes. So unfortunately, it would be a really fun experiment to do if you could actually drop stuff into a black hole and watch what happened and use that to test theories of how black holes work. But luckily for us, the black holes are too far away. If they were close, we'd probably be in trouble. We might be in a little bit of danger if a black hole wandered too close to us.
There's a question here.
Does the black hole ever die?
Does a black hole ever die? Excellent question. So the answer is yes, but it takes a really, really long time, much longer than the age of the universe. So one of the ideas that Stephen Hawking is most famous for is the idea of something called Hawking radiation. And this is the idea that due to an interesting quantum mechanical process that happens on the surface of black holes, right at the event horizon, there's a very steady but very slow stream of elementary particles and photons of light that are streaming away from the black hole. And the black hole gradually, very slowly evaporates due to this process. Now, for the kinds of black holes that we know of in nature, that evaporation is so slow that we would never be able to see it. You would have to wait far, far longer than the age of the universe in order to actually be able to detect any change in the mass of a black hole due to Hawking radiation. But in fact, once black holes start to become smaller over very long timescales because of this process, the rate of Hawking radiation accelerates, and a very small black hole will actually evaporate explosively in a bright burst of light and then just cease to exist. So at the end of the universe, long after there are no more stars, no more luminous stars or anything, the last sources of light in the universe, we think, are going to be black holes that are exploding in a burst of Hawking radiation.
Something to consider.
Along those lines, considering the evaporation of the hole, the jets that come off of supermassive and regular black holes, is there since we don't really know the physics of the center of the singularity, is it more likely that that energy, because it's going at the speed of light, I would assume out, is accelerated in that point?
Yeah, so that question is about something that I didn't really talk much about in this particular talk, but some quasars have what are called jets coming out of them, which are beams of very hot plasma moving at almost the speed of light, oppositely directed, coming essentially out of the north and south pole of the black hole. And the question is, where does that come from? The answer is that the acceleration of those jets is very complicated and has to do with magnetic fields in the inner part of the accretion disk and magnetic fields in the environment of the black hole. And material from the accretion disk can get swept up in those magnetic fields around a rotating black hole and channeled out in these jets. But that was material that never made it into the black hole in the first place. So that's not material that made it past the event horizon. Those jets are coming from material that was coming in through the accretion disk and then got channeled outward by magnetic fields.
So over here.
As I understand it, back here at home, as the Earth rotates around the sun, you're saying the sun is slowly rotating around a black hole at the center of Milky Way.
Yes.
Is this a fact or a theory?
Okay, so we know this. It is a fact that the sun is part of the disk of our Milky Way galaxy that's orbiting around the center of the Milky Way galaxy. Now, the fact is that what I showed you is that at the center of the Milky Way galaxy, in our galaxy, from observations done by the UCLA group, we know that at the center of our galaxy, there is an extremely compact object, much smaller than the size of our own solar system, that has a mass of 4 million solar masses. So if you can imagine 4 million times the mass of the sun packed into an object that is comparable to or smaller than the size of our own solar system, that is a fact. That is known to exist. Now the question is that a black hole or could it be something else? Is there any other object in nature that could have that much mass packed into such a small volume? And the answer is we don't know of anything that could actually do that. Physicists have tried to come up with models for, say, blobs of balls of elementary particles or other kinds of objects. It's very, very difficult to come up with any kind of a realistic physical model for anything that could be that massive and that compact. And for example, if all of that mass was in something, you might imagine that all that mass was in some other dark kind of object that wasn't giving off any light, like say just planets that weren't orbiting around any star, but just a bunch of rocky planets. Well, if you had that much mass in rocky planets or anything else, baseballs or any other kind of matter within such a small volume, if you had 4 million solar masses worth of it in that small of a volume, it would collapse down to a black hole, according to the laws of general relativity. In some sense, we can't prove that it's a black hole, but we have a high degree of certainty that it must be because we don't know of anything else that could be that extreme.
Yeah.
What's a micro black hole?
Okay, there are a couple of different terms that, are you thinking about the black holes that might be created in particle accelerator experiments? Okay, so this is something that's been in the news a little bit because of the turn on of the LHC in Switzerland, this particle collider. The basic idea is it's thought to be, by particle physicists, possible but not hugely likely that in some very energetic collisions of elementary particles, you could squeeze enough energy into such a small volume that you would actually create a tiny microscopic sized black hole. So you can create a black hole essentially of any mass just by squeezing enough matter or energy down to a small enough volume. So you can do it with elementary particles just as you could do it with a star if you can squeeze the mass and energy down to a small enough volume. Now, it's thought that if a black hole like that was created, it would evaporate explosively and almost instantly in a burst of Hawking radiation. So that would be the observational signature. If they see something that looks like this little burst of Hawking radiation in the detector, it's a difficult thing to look for, but the physicists there are going to be looking for that. And they could conceivably find evidence that their experiment is creating little microscopic black holes.
Emphasize there a little burst of Hawking
Yes.
radiation.
Yes.
One last question, we'll wrap up here.
On the subject of the 0.1% mass, you said that was relatively constant in samples you've seen. But shouldn't that increase with time because the black hole is continuing to grow?
Yes, excellent question. So the question is whether that 0.1% of the mass in the black hole goes up over time because the black holes are continuing to grow. And the answer is yes, absolutely. So that 0.1% is for basically local galaxies in our neighborhood of the universe where we're not looking back to very large times in the past. So as we look to large times in the past, actually, there are a lot of groups who are working on that very question, trying to understand if we look out to higher redshifts, out to farther in the past, what was the ratio of black hole mass to host galaxy mass? And it seems to change over time in the sense that the observations are telling us that as we look back in the past at luminous quasars and try to estimate the masses of the black holes in those quasars, the black holes were more massive than 0.1% of their host galaxy. And the idea is that it seems observationally from what we can see that the black holes probably grew earlier and then the galaxies became more massive as more gas piled onto the galaxies and formed more stars gradually over time. There's a lot more to be learned about that, but that's a very active question for current research.
Okay, so I think Aaron will be happy to stick around to talk with people a little bit. If you have additional questions, why don't we do that? Let's thank Aaron again for a great talk.